Welcome back to Advent of Code 2018. We're on problem 8, day 8, memory maneuver. Looks like something to do with trees. Tree problems. I like tree problems. Trees and graphs. I would say that's my probably the area I have highest skill in. Maybe. I don't know how to measure that. Okay. The sleigh is much easier to pull than you'd expect for something its weight. Unfortunately, neither you nor the elves know which way the North Pole is from here. You check your wrist device for anything that might help. It seems to have some kind of navigation system. Activating the navigation system produces more bad news. Failed to start navigation system. Could not read software license file. Navigation system's license file consists of a list of numbers, your puzzle input. Numbers define a data structure which, when processed, produces some kind of tree that can be used to calculate the license number. Hello, DIJ. Look at the sun. Oh, for navigating. Well, would that help? We don't know what part of the world we're in, so I suppose it would sort of help. Or do we? I don't know. Oh, we do know roughly what part of the world we're in, yeah. We just don't know what exactly where we are. Oops. The navigation system's license file consists of a list of numbers. The numbers define a data structure which, when processed, produces some kind of tree. I already read that bit. The tree is made up of nodes. A single outermost node forms the tree's root, and it contains all other nodes in the tree. Okay. Specifically, a node consists of a header. Are we going to make a hex tree? One of these days. In coding game, I did actually finally have an actual hex tree for an actual use in the last competition. Yeah, one of these days we're gonna have a hex tree, I'm sure. In Advent of Code. The tree is made up of nodes. A header which contains the quantity of child nodes, the quantity of metadata entries. So metadata entries are just like a data which is stored in this node, and we have pointers to every child node. Makes sense. Okay. Each child node is itself a node that has its own header, child nodes, and metadata. Okay. Example. A, which has two child nodes B and C, and metadata entries 112. I don't understand this top row here. Let's have a look at the input as well. The heck? Ah, so it's... Oh, so they're not line separated. They're all kind of, you have to parse them integer by integer. So 9. So the header is the first two numbers. 9 and 11 here. And then the 9 child nodes are the next 9. And then the 11 metadata entries are the next 11. That's how it works. And then you go on to the next integer. Fine. So it's a stream. So it just means more work parsing, but fine. The row looks like child nodes. Because A has a 2 and C has a 1. Still don't fully get what these hyphens are, what this graph is trying to tell us. 1, 1, 2 is there. A 1, 1, 2. B has 10, 11, 12. C has 2. So these numbers at the end are their data, but why is it? Why have they drawn this graph like this? I don't understand. What are all these hyphens for? D has no child nodes and 1 meta entry, 99. So what's this 0 and this 1? Oh! Okay, that's the 0 and the 1 there. So D, 0, 1, and 1 entry, 99. Okay, yeah. A, 2, 3, 1, 1, 2, 2, 3. But then... Oh, it's this... Okay, fine. It's a strange sort of graph. These things belong to B and C, so they're not counted as A. So if you exclude them, you're left with 2, 3, 1, 1, 2. I don't know why they've done it like this. I don't think we need to worry about that kind of formulation. It doesn't change the way that the structure of the tree. Okay, it's just a... I'm sure there are better ways. Just, I don't know, just a normal tree where you have a node pointing to another node and each node has a list of its data. Anyway. Okay, the first check done on the license file is to simply add up all of the metadata entries. In this example, that sum is this. So, part 1, we don't have to do anything with trees. We just literally add up all these numbers here. Okay. Fine, let's just do that. I mean, part 2 is going to need the tree, obviously, but... And my coffee is ready. Second. Alright, I bought some new Vietnamese coffee today. This seems to be some sort of drip filter thingy. Not sure how to use it. It's hazelnut flavor. So basically we just need to go through the integers one by one, following this header process, and every time something is a metadata entry, just add it to a total, and that's it. Could be an easy part one. So it's like one of these packets where you've got to construct like a little thing and put it over your cup. God damn it. It's too small for my cup. No, just about fits. Right, leave it to drip. Drip for a while. That coffee seems like more work than it needs to be. I mean, this is, as far as drip coffees go, this is the easier version because it's just like disposable packets. But if you use the proper Vietnamese, like you have a separate like metal kind of drip device, which of course you've got to clean, which is a pain. But it doesn't use plastic and paper, so I'm not exactly being environmental friendly here. Alright, I'll leave it to drip for a while. Okay, so... I'll just keep my Mr. Coffee from like 1985. Is that instant coffee? Okay, so we need to zoom in a bit. So we've got this huge array of numbers. Oops. It's one row. A brand of copy machines. Oh, okay. Do you... Alright, so... It's just one line, so... We just have to... do this. Nums equals f dot read line, one line, dot split. Equals map int. So map each of those to an int. Or just do a list comprehension, then we'll make sure it's a list. Oops. Int x for x in okay. Total equals 0. So now we have to follow this process basically. while... Okay, so... I equals 0. While I is strictly less than length of nums, so while we don't run out of numbers... So... The first... Okay, so the first is the quantity of child nodes. So, num childs. In programming, I always use childs instead of children. I just think it makes, from a programming perspective, it makes sense. One child, two childs. This puzzle is definitely helped by visualization. Yeah. I don't like the visualization they've done, but it's... I mean, I see the sense in it. Fortunately for now, we literally just have to add up all the data, so we can worry about what we do with the tree in part 2. So numchilds equals nums I. And then we do 4 in range numchilds. So now the next block, we do nothing. We do nothing. We just add 1 to I because we don't care about the children. And now we read the data. So it's going to be num data. And then for each data entry, total plus equal nums I. Put that into the total. Add 1 to I. And then we should be on the next integer ready for the next repeat of this. So we do nothing because we don't care about the children. Is that how I worded it? Fair enough. I remember when I studied operating systems, you got all these concepts. You got children, you've got zombies. Zombies are like processors, child processors whose parents have... What's a zombie process? Well, you've got orphan processors, like a child processor who's lost its parent. And then you've got zombie processors, which also means something. You have all these different analogies, types of processors, and what can happen. Grandfather processors, ancestors, descendants. Alright. Then that's it. Just print total. Two, 4, 3, 4, 6. Alright, got it wrong, even though that seems like such an easy problem. Alright then, test it on the example. Can't think how I could get that wrong. List index out of range. Oh. Oh, now I see why they made that graph look like that. Because they wanted the first row to look exactly like it would in the file. Because they don't actually have it listed anywhere else. Okay. That makes sense then. So this row I just copied from that graph they did. That's exactly what it looks like in the input. Typo in word childs. Why have I got spelling check on? Turn this... I thought I did this before. How do I turn spell check off? Spelling. No, what is this? I don't want spelling. Configure spelling inspection. Proof. Ah! I didn't find this menu before. There we go. There we go. Okay. Why would I have spell check in a IDE? I mean, there's cases where you would want spell check if you have comment-heavy code, in which case you want the comments to be spelled correctly. It does help, especially when searching for things later. If you're searching for something with a certain name, but you haven't spelled the name of that thing correctly, then later on another developer's not going to be able to find that. Okay, index out of range? Why? Alright, let's run this through by hand and see what happens. So, we take the 2. Of course! I've done this in the wrong order. Okay, so numchilds is that, I plus equal 1. Then we get the num data. I've done this in the wrong order. That's the header. Those 2 are the header. And then we do the 2 for loops, one after the other. That's why it was wrong. Still wrong. So numchilds equals num's I, so that's going to be the 2. Num data equals num's i's. So we add 1. Num data equals num's I, so that'll be the 3. And then for that in range numchilds, we add 1. For that in range num data, we add 1. So we're looking here, and then we go 1, 2, and then we go 1, 2, 3. Yeah, so we should now be looking at the 1. While i's length and length nums. So then we do it again, so it's 1, 1. So 1, 1. Then we're looking at Then we're looking at 99. Hang on, this isn't right. 2, 3. 1, 2. 1, 2, 3. Then we've got 1, 1. 1, 1. Oops. Have I? I'm gonna have to have a look at this again. Oh, of course. That's... They've sandwiched this in a weird way. That's the whole point of this weird graph. Because not only have they... Okay. A's data is at the end there. Oh, this is This is actually a bit more complicated then. So the point of that weird graph was just to explain the weird input system they're using here, where it's all sandwiched into one line. So you have nodes within outer nodes, and all the data for the 2 and the 3 are not the next 3 digits. They're actually at the end here. The parent's data is after all its children. Oh dear. Okay, fine. So we need to use recursion here. Okay, I get it. So, a child means we open up a new recursive call, and we get the data and the metadata by the same process. And when the childs are closed off, we recurse. We return to the parent process. Okay, I get it now. So, yay, recursion. Okay, this is actually not an easy part 1 then. I take it back. Oh, my drip coffee should be done now. Well, I got the coffee just in time for making recursion. Okay, so So we want a process here that it will be called recursively. So we want define, extract, meta, just call it data, extract data for a given index. Now this says I want to extract all the data for the process, the node that begins at this index. I want to extract its data and the sum of all the metadata of all its child processes. So we just make one call for extract data with I equals 0, and it's gonna call extract data recursively on each individual child. Yeah, it's always fun when the problem is at first glance is really easy. Yeah, I did not stop to look at how the input is actually formed, but yeah, that's exactly why they listed it. Okay, now the visualization for that makes complete sense now. I thought they were listing it in node by node order, and then for some reason they jumbled it up for this weird graph. Okay. Extract data I. Okay, so we're looking at, alright, so it's similar to this. We say okay, so it's like this. We say num childs equals nums I. Num data equals nums I plus 1. Okay. So that's the number of childs and the number of data. Okay, so for so let's say for j in range num childs, so the start of each child, hello Mara, at this rate you'll catch up before Xmas. I've got what, 2 years worth left. Yeah, I could do that if I do one in October and one in November, but I'll have to, I don't know, I'll have to do them at a fast pace because I don't really want to really be spending the whole of the 2 months doing this. Yeah, it's doable. I think it's doable. Alright, so the start of each child will be so we want to sum the recursive extract data on index I plus 2 plus j. So for j equals 0, it'll be I plus 2. No, this is wrong. No, wait. No. We need to return two things from this. We need to return the data, and we need to return the index we finished at, because we don't know how long the recursive chain of childs is. We don't know what index we'll end up at. So we can make total a global variable. Alright. Say j equals I plus 2. So we know the first child starts here. In range num childs. So we're going to do j equals extract data I plus 2. So what this does is it calls the extract data, it adds all the data recursively into total, and it spits out the finishing index, i.e. the index after the first child. So now we've updated and we're ready to take the next child. So we do that. And then we've dealt with the childs. We should now be looking at the rest of the data. So for k in range j to j plus num data, total plus equal nums k. So add each of those pieces of data into total. Alright, get rid of all this. Let's take this down here. And then we return j plus num data. For this to work, we have to now return the end pointer. Okay. So to actually call it, we need to do extract data 0. That just runs on the parent node. And then print total. 68. So that's the example. No, we should be getting 138. Damn it. Missing 70. Okay. So let's print some things here, see that we're using the right indices. So let's say print I numchilds. So this is checking we're getting the right headers. Zero, 2, 3, correct. 203, 203. What the? Ah. So we're calling this child twice. We're not updating J correctly, which means we're not returning. Can you tell it to print what it thinks the metadata is? Yeah, I can do that as well. But it seems we've got the indices wrong here, so we found the problem. Advent of code challenge. Solve everything with hex trees. I mentioned that earlier. We might one day, for Advent of code at least, get to use a hex tree. I did already use one for coding game. Alright, is this wrong then? This seems we're not correctly updating J. So J is I+2. Oh, wait, no, we shouldn't be using I+2 here. We should be using J. J is not, it's not using the new J each time. That's the problem. 138, there we go. Alright, big example. 47464. That's gotta be right, if the small example was right. So it's basically double what I had before. Correct. The second check is slightly more complicated. You need to find the value of the root node. The value of a node depends on whether it has child nodes. If a node has no child nodes, its value is the sum of its metadata entries. Okay, we know how to do that. If a node does have child nodes, the metadata entries become indexes. Shouldn't it be indices? Which refer to those child nodes. No, indexes and indices have two subtly different meanings. I think indexes is correct here. A metadata entry of 1 refers to the first child node. I see. Child node can be referenced multiple times and counts each time it is referenced. Entry of 0 does not refer to any child node, okay. Ooh, that's not too hard to code, it's just... this paragraph here is a little wordy, but it's... okay. I think I get it. So, we make another recursive call as before. Where we're computing value instead of just the sum of metadata entries. Okay, so Alright. Okay, so we need... I might only have time for this one problem. Part 2, we basically do this recursive call again. No, do a new recursive call, so we don't care about total. It's going to be called get value. Don't need global total. Get value. Alright, so get value for the node I. Okay. So again, we get the child's, extract the child's and the data headers. As before, okay, then we set j equal I plus 2. For each child, j equals... Okay. So we need a new array here. Child values equals array. So we need to put the values in here. So our method is going to return a pair, which is the value and the end pointer for that node. So value, let's say child value j equals get value j. And child values dot append child value. Okay, so we now have an array of all the child values which have been computed recursively, and we're updating j. Technically, indexes and indices are the exact same. Indexes is just an anglicized version, where indices stays true to the Latin. Yeah, I guess that makes sense. But maybe there's some cases where, like, if you were using index other than as a pointer reference, like index... Okay, I was playing Halo the other day. There's the index, which is the key that you're trying to get, which destroys Halo or whatever. So that's not a pointer in an array, but rather an actual key called an index. Would you say indices there, or would you say indexes if there were more than one keys? I feel like that would be indexes, because it's not the same noun. But yeah, this one I guess is index as in a pointer, like you would use in a dictionary. So it should be indices, or indexes is fine too, I guess. Yeah. But there's probably some cases where you would stick with indexes if you were using other meanings of index. I don't know. Okay, so we've got the child values now. Now we've got the data. So we want data equals an array. Data dot append nums. I see. All right. Actually, data is just nums from j up to j plus num data. But we don't actually need to do this. Okay, so now we've got the child values and we've got the data. Alright, so now there's two cases. If not child values, so there are no children. Or just to be completely accurate, let's say childs. Then in this case, they said some of its metadata entries. Okay. So we want to return sum of data, and then we also want to return j plus num data as the end pointer. So at this point, we are doing the more complex version, which is if we do have child nodes. So what do? We look at each metadata entry. Okay, so we say v equals 0. For d in data, so they're using one indexing here. So 1 refers to the first child node. Okay, so child index equals d minus 1. If now it should be 0 less than or equal to child index is strictly less than num childs. If it doesn't fall in this range, we skip it. If it is in this range, then we add that specific child value. So it's going to be child values of this child index. This is an interesting... Oops, child value v must equal that specific child value. And then we return the summed v, which is our upper value for this node, and j plus num data. Okay. So we just want the value of the root node, don't we? So print get value 0. And we could actually just extract the first entry. Okay, so it says 23054. Do we trust the recursion here? Might need to test it on the example. Yay! I mean, the structure of the recursion for part 1 was right, so structurally it was sound. It was just a case of getting the right indices for part 2, really. That was a pretty good problem. I know people have different approaches to recursion. I always do it this way, where you write a recursive method. Some people like to do things iteratively, so that means they do for I in range. Well, they do it the C++ style, so they'll probably transform this data into a... Well, in this case, it's a bit tricky to do it that way. You would have to... I don't know, build a tree data structure and then go through that data structure from the child nodes backwards or something. I think this quick recursive process is the way to go. If you're working in a company or something making software, you would not do this because this is unpredictable amount of stack usage. So in real software, you always do the iterative approach, so that you're never using stack memory. You're only doing one thing at a time. But it's the nice, quick mathematical way of doing things. It's just, you're just assuming the stack memory won't run out. So if this had 1000 levels of depth, which is very easy to reach if they just added some more data here, then we would run out of stack memory and you'd get Python recursion limit hit. In which case you would have to rewrite it in an iterative way. So you would need to build a tree data structure, and then you would need to make a pass through that tree from the children backwards, filling in each of their values, going back through the tree, so that you're never really keeping a pointer to like several levels of depth in terms of parents. You're only doing one thing at a time. Yeah, it's a good problem. Alright, I need to get to the gym. So that was just one problem for this stream. Let's have a look at stats and stuff. Oh, that was 8. No, I always forget how the... 3 minutes 45 to solve both. I mean, that's pretty believable. Recursion problems are always really quick to solve. If you get what the structure is supposed to look like, it's really quick to write recursion. No, not this one. Yeah, so... because of a bug in day 6... Oh, I see. So day 6 was bugged on release. Difficulty-wise... seemed alright. Yeah, so I got these two. If I do those in October and November... that's... yeah, I think I can do that. Alright then. That was day 8, although one stream for one problem is not a hugely fast rate of completion, but I didn't have much time today. Alright, thanks for watching. I'll try and do another 1 or 2 problems tomorrow.